This is section 6.7, Roots and Zeros. Our objective today is I can state the number and types of roots of an equation, and I can find the zeros of a function. In example 1, we're going to solve each equation and state the number and types of roots. On A, we have x squared plus 6x plus 9 is equal to 0. So the first thing we want to do is factor. So if we go ahead and factor this, we're going to have x plus 3 times x plus 3. Because 3 times 3 equals 9, and 3 plus 3 equals 6. So, if we go ahead and figure out these, we're going to set them both equal to 0. So we're going to have x plus 3 equals 0, and x plus 3 equals 0. If we solve for x in both of these cases, we're going to end up with x equals negative 3, and since the second equation is the same as the first, we'll also end up with x equals negative 3. So, since we got x equals negative 3, that means it's going to be a repeated root, and so there's only going to be one real root in this case. And so, since the graph of the equation touches the x-axis at x equals negative 3, that's the only place that it's going to touch the x-axis, and so the graph isn't going to cross the x-axis. Instead, it's going to look something like this. So if this is negative 3, we're going to have a point there, but it's going to go up, so it's never going to actually go across the x-axis. Let's go ahead and look at example B. We have x cubed plus 25x, and we can go ahead and factor this. First, I'm going to take out a GCF, so I'm going to be left with x squared plus 25. So if I go ahead and solve each of these, I'm going to have x equals 0, and I don't have to solve anything. I'm going to have x squared plus 25 equals 0. And if I solve that, I'm going to subtract 25 from both sides, so that I have x squared equals negative 25. And I'm going to take the square root of both sides. So remember, when we have a negative under the square root, that's going to mean we're going to have an I that we're using. So x is going to be equal to plus or minus 5i. So the equation is going to have one real root at x equals 0 and two imaginary roots, positive 5i and negative 5i. The graph of this equation is going to cross the x-axis at only one place, and that's going to be at x equals 0. In example 2, we're stating the possible number of positive zeros, negative real zeros, and imaginary zeros of f of x equals x to the 6th plus 3x to the 5th minus 4x to the 4th minus 6x to the 3rd plus x squared minus 8x plus 5. So the first thing we want to do, we know that because f of x has degree of 6, it has 6 zeros, either real or imaginary. So we know that the total is going to be 6. We're going to use the rule of signs to determine the possible number and types of real zeros. So first we need to count the number of changes in sign for the coefficients of f of x. So we're going to look, and we have positive x to the 6th. Then we have positive 3x to the 5th. We then have a negative, so here's a change of sign. We go from positive to a negative. So I'm just going to go ahead and put a little check mark here that counts as a change of sign. Then we move from negative 4x to the 4th to negative 6x to the 3rd. That's not a change of sign, both negatives. Then we move from negative 6x cubed to positive x squared. Again, that's another sign change. We're going to put a check for that. Then we move from positive x squared to negative 8x, another sign change. And then we move from negative 8x to positive 5. So again, another sign change. So that's going to be 4 sign changes that we're looking at. And we know that since there are 4 sign changes, there are either 4, 2, or 0 positive real zeros. So I'm just going to mark that down. 4, 2, or 0, positive real zeros. Next thing we want to do is count the number of changes in sign for the coefficients of f of negative x. So all I've done here is gone through and plugged in negative x for each of the x values. And then we want to go ahead and rewrite this to see what that actually means. So here we're going to have x to the 6th power minus 3x to the 5th minus 4x to the 4th plus 6x cubed plus x squared plus 8x plus 5. And we want to go ahead and count the number of changes that there's going to be here. So here we go from positive to negative, so that's going to be a sign change. I'll put a check mark. Then we have negative 3x to the 5th, negative 4x to the 4th, no sign change. Negative 4x to the 4th, positive 6x to the 3rd, another sign change. Then 6x to the 3rd, positive x squared, no sign change. Positive x squared, positive 8x, no sign change. Positive 8x, positive 5, no sign change. So there's two sign changes, so there's either going to be 2 or 0 negative real zeros. 2 or 0 negative real zeros. I'm going to mark that down. And so now we can go ahead and create a table based off of this information. And we need to put all of the combinations that we've came up with. So I'm going to go ahead and chart this out here, make it into a nice table for us. We know that the total number of zeros has to be 6, no matter what we do. So we know that positive real zeros is either going to be 4, 2, or 0. So I'm going to go ahead and mark that down. 4, 2, or 0. And then we know that our negative real zeros is either 2 or 0. So I'm going to go ahead and pair the negative zeros, 2, 2, 2. And then we also need to use this 0 over here to be paired with each of them. So I'm going to go ahead and mark those down. 0, 0, and 0. And then I'll rewrite my positive real zeros, 4, 2, and 0. That gives me every possible combination of the things that I came up with. And then since we know that the total of numbers needs to be 6 each time, we know that the imaginary zeros has to make us go up to that 6. So here if we have 4 positive real zeros and 2 real negative zeros, then we know that we're going to have 0 imaginary zeros because we know that it has to add up to 6, and 4 plus 2 is 6. On the second one, we have 2 positive real zeros, 2 negative real zeros, which means in order to have 6 total zeros, we're going to have 2 imaginary zeros. On our third one, we have 0 positive real zeros and 2 negative real zeros, which means in order to have a total number of 6 zeros, we're going to have 4 imaginary zeros. On the third one, we have 4 positive real zeros, 0 negative real zeros, which means we're going to have 2 imaginary zeros to give us our total of 6. On the next one, we have 2 positive real zeros, 0 negative real zeros, which means we're going to have 4 imaginary zeros to get our total of 6. And on the last one, we have 0 positive real zeros, 0 negative real zeros, which means we'd have to have 6 imaginary zeros to have the total of 6. In example 3, we're going to use synthetic substitution to find zeros. It says it wants us to find all of the zeros of f of x equals x to the 4th minus 18x squared plus 12x plus 80. So the first thing we're going to do is determine the total number of zeros. And since f of x has the biggest degree of x to the 4th, we know that the function is going to have 4 zeros. So now we want to do the same thing we did in the last example. We want to look at the number of sign changes. So in f of x, we know to get from positive x to the 4th to negative x squared, there's a sign change. To get from negative 18x squared to positive 12x, there's a sign change. So there's going to be 2 sign changes here. Then we want to look at f of negative x. when we plug in negative x, anywhere there's an x, we're going to end up with x to the fourth minus 18x squared minus 12x plus 80. And we can see that we have a sign change from x to the fourth to negative x squared. We have a sign change also from negative 12x to plus 80. So because there are two sign changes for the coefficients of f of x, the function has 2 or 0 positive real zeros. Because there are two sign changes over where we're looking at f of negative x, we know that there are 2 or negative real zeros. Thus, f of x has 4 real zeros, 2 real zeros and 2 imaginary zeros, or 4 imaginary zeros. So we have to find out which one of those it is. So, what we're going to do, we're going to make a table. And we want to determine the number of real zeros. So we're going to list some possible values and then use synthetic substitution to evaluate f of x for real values of x. So I went ahead and created a table using some different values, negative 3, negative 2, negative 1, 0, 1, and 2. So what we're wanting to happen here, we're wanting this last column over here to be 0. That's what we're wanting. And so the way that we're going to figure these out, we're going to use our synthetic division that we've used before. So in this case, we're going to use that negative 3, that negative 2, that negative 1 over in our little box on the left-hand side. So first I would use negative 3. And I'd plug in 0, 1, 0, negative 18, 12, and 80. And if I'm doing my division, I'm going to want this number right here to be 0. So if I do negative 3, remember my 1 comes down, so 1, and then I have negative 3 times 1, which gives me negative 3. 0 plus negative 3 is negative 3. Negative 3 times 3 is 9. Negative 18 plus 9 is negative 9. Negative 3 times negative 9 gives me 27. And then, if I have negative 3 times negative 9, I'm going to get 27. And then adding down, 12 plus 27 is going to give me 39. And then negative 3 times 39 gives me negative 117. And then 80 plus negative 117 is going to give me negative 37. And that's not 0, so we know that that isn't going to be one of our real zeros. But that's what you're going to do for each of these. So what's going to go in our table here are these numbers down here. So if I go ahead and write these out, I have 1, negative 3, negative 9, 39, and negative 37. And I'm going to do that type of division for each of these to see where am I going to get a 0 for this last column. So when I'm doing negative 2, I'm going to have 1, negative 2, negative 14, 40, and 0. So right away I can see that this is going to be one of the values I'm looking for. Let's go ahead and fill out the rest of these just so you can see how it's going to look. So in negative 1, we're going to have 1, negative 1, negative 17, 29, and 51. So that one's not going to be one of them. With 0, we'll have 1, 0, negative 18, 12, and 80. Again, the remainder's not 0. With 1, we're going to have 1, 1, negative 17, negative 5, and 75. And with 2, I'm going to have 1, 2, negative 14, negative 2, and 76. So the only one I can use from this table is the negative 2. So from the table we can see that 1 0 occurs at negative 2. And since there are two negative real zeros, we can use synthetic substitution with the depressed polynomial. So that's the new piece that we have, and that's going to make it a little easier for us to find that second negative 0. So let's go ahead and do that. So we're going to be doing the same thing we did the first time, still setting up a table, still using our synthetic division. So let's go ahead and start off with negative 4. Remember, we'll bring our 1 down. We'll have negative 4 times 1, which is negative 4. Negative 4 plus negative 2 is negative 6. Negative 4 times negative 6 is positive 24. And then if we add straight down negative 14 plus 24, we're going to get positive 10. And then negative 4 times 10 is going to give us negative 40, which we're kind of missing our last row, but we have negative 40 plus the 40, and that's going to give us the 0 that we need. So we can go ahead and fill this in. And since we did get 0 as that last number, we don't really need to do anything else, because we know that x equals negative 4 is going to be our second negative 0. So now we know that x equals negative 2 and x equals negative 4 are two of the values that we're looking for. And we also now have this three-piece that we can work with. And so we're going to be able to use the quadratic formula with that. So we're going to have, we know we're going to use x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we're going to be using our new equation, x squared minus 6x plus 10. And if we work through this, we know that a is 1, b is negative 6, and c is 10. So if we plug all of those values in, we're going to have negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 10 all over 2 times 1. And if we simplify that all the way, we're going to have 3 plus or minus I. So we know that the function has zeros at x equals negative 2, x equals negative 4, x equals 3 plus I, and x equals 3 minus I. So in the last example, example 4, it says to write a polynomial function of least degree with integral coefficients, the zeros of which include negative 1 and 5 minus I. So if 5 minus I is a 0, then 5 plus I is also a 0, according to the complex conjugates theorem. So we know that x plus 1 and x minus 5 minus I and x minus 5 plus I are factors of the polynomial. So we want to go ahead and write this out as factors. So we're going to have p of x equals x plus 1, x minus 5 minus I, and x minus 5 plus I. So then we want to start factoring these things. We want to start regrouping. So if we go ahead and regroup, we're going to have p of x equals x plus 1 times x minus 5 minus I times x minus 5 plus I. And the reason that we went ahead and did that, we wanted to be able to group the x minus 5's together. So if we group the x minus 5's together, we can now rewrite this as x plus 1, x minus 5 squared minus I squared. So then we're going to have x plus 1, x squared minus 10x plus 25 minus negative 1, because we know that I squared is equal to negative 1. And then if we go ahead and simplify this, we have p of x equals x plus 1 times x squared minus 10x plus 26 And if we go ahead and multiply all of these numbers through, we're going to have p of x equals x cubed minus 10x squared plus 26x plus x squared minus 10x plus 26. And then we can go ahead and combine like terms. So we have x cubed minus 9x squared plus 16x plus 26. And because there are 3 zeros, the degree of the polynomial function must be 3. So p of x equals x cubed minus 9x squared plus 16x plus 26 is a polynomial function of least degree with integral coefficients and zeros of -1, 5 minus I, and 5 plus I.